All right, thanks everybody. Thanks for showing up. It's great to be back in Cambridge. Some of you may not know I did my undergrad here. I was actually born in the UK, grew up here, and scarpered to the good life quite a while ago now. But it's always fun to come back. So I don't want to keep you too long. I know there's an open bar, and it's hard to compete with that. So I just want to give you a pretty short talk. First half of it, you may have seen some of this before. I just want to go over what is this RISC-V thing anyway. There's a lot of misconceptions about RISC-V still, even after all these years. I want to kind of revisit that and just see how RISC-V has grown. The second half, I want to sort of highlight what SiFive has been doing, and I think you might be a bit surprised at how far and how big RISC-V has gone. A lot of people like to say RISC-V is going to, it's good for this, it's good for that, but the reality is it's going to be everywhere and good for everything, and I'll give you a taste of that as we go through this. So I'll start off with your spiel on why RISC-V, right? When we started this project, one of the things we noticed was ISAs tied to companies. The companies come and go, and they take their ISAs with them. So, DEC was an example, pretty popular East Coast company. That's some very important ISAs. You may remember the Alpha was all the rage in the 90s. That was the hottest thing. I remember researchers building their whole world around Alpha. Then it went away, right? Thanks to business mismanagement at DEC, right? Intel, they're doing pretty well, or sort of not so great recently, but they've been around a long time, and they've had a lot of ISAs, and they also had people invest in these ISAs, and then they killed them. You might remember i860, i960. There was this thing called Itanium, when they tried to get rid of their second source competitor, AMD, by monopolizing 64-bit ISA. Thankfully, the industry said no. Microsoft and AMD came together and did AMD 64, and Intel had to license the ISA back from AMD so they could build chips, right? Spark, that was one of the early risks. That was actually an open ISA. They opened it up back in 94, made it an IEEE standard. But then Oracle bought Sun, and basically now they've closed down Spark development, so Spark is officially dead. MIPS is an interesting example. This was the classic textbook RISC. A lot of universities built all their curriculum around this, very popular. For a while, desktop machines, SGI, other folks. But it kind of collapsed, various reasons. It was sold to Imagination, then sold to a startup, Wave. They actually tried, after RISC-V, they tried to open up MIPS, except what they did was they opened it up with a lot of strings, and the next year they closed it down again, right? So they had to sell off the company, needed the IP rights. IBM Power, another pretty important RISC ISA from the 90s, sort of trickling off in relevance right now. They tried opening it up as open power, and who's doing anything with open power? Like almost, you hear nothing about it, right? And there's a lot of reasons for that I won't get into here. And then there's ARM, local boys. They did pretty good. But then they got sold in 2016 to SoftBank. And this caused a bit of a shockwave in the industry. We know this because SiFive had just been founded like the year before. We did our launch, I think, like the month before SoftBank bought ARM. And all of a sudden, everybody is, well, what's going on with ARM? Can we rely on these guys? What's going to happen? Then you saw this recent activity with NVIDIA announcing they're going to acquire them, and then that deal got shut down, and now they're trying to IPO, right? So the lesson here really is, I'm not going to pick on any one of these, but software is king in systems, right? Software is the main thing, is the main expense. So why would you entrust your software investment to a proprietary ISA? They come and go. Bad business management of the company means the ISA goes under, not for any technical fault, just because it's proprietary, right? Everywhere else in the industry, we have these open interfaces. It's just accepted practice. Like Ethernet is now accepted, that's your networking standard. In the old days, you used to have DECnet and Token Ring and all these other things, but they all died and everybody wanted the open standard. Until recently in the ISA space, there was nothing, right? And there's no, as we could tell, there's no good reason for that. They just had, historically, we just didn't have anything open in the ISA space. Now, the other theme I want to get at today, and I'll bring this back with SiFive later, when you build an SoC, a lot of people fixate on the apps processor, because most of the lines of code, numerically, most lines of code run the apps processor. But there's all these other things you do on the processor: graphics, image, radio, audio, security, power management. And it's not unusual to find there's over a dozen ISAs on a single chip, right? Each of them has their own crummy software stack, right? And they're crummy because it's a small market. They don't have the investment to build a good software stack. So why does this happen? Well, one reason it happens is the apps processor ISA is just too big and too inflexible. It's not designed to be the basis of like a good audio DSP, right? It's designed as an apps processor. Another problem is you cannot use the IP. If it's proprietary, you can't use that ISA in building your own IP block. Like I cannot build an IP like an audio DSP based on ARM and sell it. I'm not allowed to. Only ARM can sell IP based on the ARM ISA. So what happens is you put an SoC together, you find this IP from somebody, they've had to put a controller in there, they've had to use their own one, you now have their software stack driving that thing that they have, right? And so they're forced to use proprietary ISAs. This is an example where proprietary ISAs are causing fragmentation. All these different ISAs in one chip coming from different places. And the worst example is when your own engineers decide they want to build a core and come up with their own ISA. They all think it's easy. They took the classes, they read Dave Patterson, John Hennessy's book, they figured out how to port GCC. The first one looks really good, and then you have a success, and then you need to support this thing, and you realize how much work the software support for any ISA is. So that's the worst thing. If you're a manager, don't let your engineers do that. That's like the worst thing you can do is let them design their own ISA. So there's lots of ISAs in one chip. That's another problem in the industry. So do we need all these different ISAs? Do they got to be proprietary? Do they have to keep disappearing, right? And obviously the premise of RISC-V is what if there was just one stable, free, and open ISA everybody could use for everything? And that's really the idea. And so we started this, as a university project. This is like ancient times now, but 2010, we were deciding to do a new set of projects. We needed to pick a new ISA to build our research infrastructure around. And in my group, a bit unusual, we actually do the research, we do simulators, but we also build chips and fabricate microprocessors in my group. So we needed something we could actually build. So the obvious choices would have been, x86 and ARM. x86, just impossible. And if your advisor at a university tells you to go build an x86, you change advisors. You don't do that, right? It's just like crazy complex. And also, we wanted to share the IP. So we build it, other universities use our material, we won't be able to give it to them. And we couldn't do that. Even if we had a special arrangement with Intel, we couldn't share an x86 softcore with other people. ARM, to paraphrase Doug Adams, it's mostly impossible. So IP issues are still there. And when we started back in 2010, we wanted a 64-bit ISA, and ARM had not released a 64-bit ISA then. This was before ARM v8 came out, right? And it was also a pretty complex ISA, ARM v7. So we didn't want to do that. So we decided we'd do our own. It'll be a 3-month project over the summer. I just want to give a shout out to the main, so Andrew Waterman, Yunsuk Lee, two of the other co-founders of Sci-Fi, Dave Patterson, were the main people involved in defining RISC-V, but there was actually a whole bunch of other folks who helped out along the way, but they were the main folks. So it took us a little while, so 4 years later, we finally did this 3-month project. But it took that long, we didn't just sit in the corner pontificating about ISA design. We did a bit of that, but along the way, we also did several implementations all the way through silicon. We ported compilers, we ported operating systems, and we basically iterated over those 4 years, taught classes as well. And then finally, we figured out it was good enough to broadcast to the world. So it's called RISC-V because it's actually the 5th iteration of RISC. And this was Dave was always upset that he'd given up on the RISC trademark because RISC was actually the Berkeley project. It wasn't the whole, it's like Hoover is a vacuum cleaner, but everybody says they're hoovering now, right? It's like everybody says they have a RISC chip, but actually RISC was the project at Berkeley that Dave was leading. So RISC-1 and RISC-2 they did back in the early 80s. And then the follow-on projects they did, SOAR and SPUR, they called them SOAR and SPUR, but we went back and renamed those 3 and 4. And then RISC-V is the 5th one. And actually there's a lot of similarity between RISC-V and RISC-4 encoding. If you want to do some instruction set archaeology, you'll see some similarities. So it's not an accidental thing that it's called RISC-V. But the one difference between RISC-V and the others is all the others were done for one implementation. It was a one-off, here's an ISA, here's a chip, done, right? RISC-V, this was the first one we did in 2011. It was a 64-bit core we built in 28 nanometer FDSOI. But that was only the first. Since then, we've done dozens and dozens at the university and out in industry. There's now hundreds, and I think there's well over 100 open source RISC-V cores available to download. Plus, there's probably a dozen or more commercial core IP providers. So there's many, many implementations. We designed it as an architecture, not just one chip, right? So we are pretty happy about this, and we're starting to get some pull from outside. So this is the 2014. We all got the same blue T-shirts, all descended on hot chips, the Flint Center in Cupertino, and said everybody should be using RISC-V. And we had a really, really positive reception, far above what we'd actually expected. And we learned all these things that we weren't aware of oops, oh, that's what that button does. Or we weren't aware of at the time about the problems people have been having with the other providers. Particular one thing we heard was, well, we're a startup, we talk to ARM, and it takes us between 6 months and 2 years to build a contract with ARM, and that's like kills the company. So we heard all these things that we had no clue about as naive university researchers, and other things. And it wasn't all about fees. It wasn't all about money, which is, I think, one of the misconceptions people have about RISC-V. People want the flexibility, the freedom, and the ability to move forward fast. That's one of the reasons they were attracted to RISC-V. So anyway, the other thing that happened was we got positive reception. All these companies out there said, this looks good, but we can't have it be a university project. We don't university professors, they get bored, move on and do something else. If we're going to base our whole world around this, it has to be stable. And so then we created the RISC-V Foundation as a non-profit to manage the standard, all right? And now it's transmorphed into RISC-V International based in Switzerland because it really is a global standard. And part of the main reason we moved it to Switzerland wasn't any technical or legal reason. It was mainly symbolic to indicate to people this is now a global standard. And so the membership has just grown from those early days. This is an eye chart for some of the logos on there this year. And one notable one this year, Intel finally joined RISC-V Foundation. So all the members are pledged to work on protecting and promoting this ISA. So how does RISC-V work? This is another place people get misconceptions. So the way RISC-V works is at the center of it, you have the standard managed by RISC-V International. And RISC-V International only does the specs. You don't go to it and say, where's the RISC-V core, right? That's not how it works. They just manage the specifications, go to moral compatibility suite. And that really is the key interface between software and hardware. So another misconception people have, RISC-V is not an open source processor. That's just type error. No, RISC-V is an open spec. Because the spec is open, it means you can have open source processors, right? But that's not the only thing you can do with RISC-V. Now, there is a lot of open source cores out there. Like I said, I think there's well over 100. Somebody counted those recently, 100 plus. Open source cores you can go use, everything from tiny microcontrollers up to out of order cores. They're really useful for research, academia, teaching. Product-wise, possibly some of them could be used in products, though you'd have to do a lot of additional verification in most cases to be okay with those. But the main thing is it gets it out there. A lot of people can use it. You can get started and do something with its open source cores. Now, there's also a lot of commercial core providers. So RISC-V is a commercial ISA. And there are actually more commercial core providers for RISC-V than any ISA in history. And I think there's actually more core providers, silicon providers, than any other, if you include chips as well, than any other ISA in history. The number of people commercially developing RISC-V, many, many, many vendors. And that's one of the big attractions. Also, you can build your own core. So some companies like NVIDIA for their GPUs, they design their own RISC-V core and use that as their microcontroller on the GPU. So all the GPUs shipping now have RISC-V-based controllers on there. They did a shootout where they were moving from a 32-bit to a 64-bit architecture for those microcontrollers. Previously, they had their own engineer ISA design, in-house design. They did a shootout and chose to go with RISC-V against the other commercial ISAs when going to that. And so that's an option you have with RISC-V, build your own cores. So Seagate and Western Digital, who ship a lot of units, they also build their own cores to use on those devices. So lots of choices in how you build the hardware, but what all these hardware vendors, all these hardware implementers share is the common software ecosystem. So they don't have to build their own software stack, they can use the open one. And so what's nice about RISC-V is it's very attractive to the open source community. It's an open ISA. So we had tremendous uptake from all those projects doing open source software with RISC-V. So all the mainstream projects, GCC, LLVM, Linux, BSD, all these projects, they picked up on RISC-V quickly. And even the distros. So we had Red Hat bringing up distros on QEMU. There's no silicon. And without us telling them, they would bring up the whole distro on RISC-V. So there's a lot of enthusiasm in the open source community around RISC-V. But what people may not be aware of as much is on the commercial side, there's also a lot of activity. So there's a lot of, if you go Lauterbach, Sega, IER, Green Hills, Wind River, these folks are commercial software. They're also supporting RISC-V. And the reason they are is because there's demand. So customers are building these into products. They need that commercial tool support that they used to. And these companies are responding by providing those products. So just the point of this slide is, RISC-V is an open standard. It's an open standard which allows both open source and commercial hardware and software. It's meant to be a common standard. It's just like Ethernet, right? Ethernet is everywhere. It's an open standard. You have free implementations, you have proprietary, you have software. That's what it is. It's more like Ethernet than anything else probably in the computing space. So when we started this, this is our fun goal, was just take over the world, right? Become the industry ISA for all computing devices, right? And we sort of joked about this at the beginning, and now it's happening. So this is what is happening. And I think one thing I want to point out is it's happening way faster than any of us predicted, and across more domains. And the performance levels people want are everything from what I call low to ludicrous, right? They want tiny microcontrollers for sure, but also people want as high performance RISC-V cores as any other ISA on the planet, right? That's what people want. The other thing we're trying to manage at the foundation is it's open as a community process to design the ISA, and as a result, everybody wants every feature that was in any ISA ever all in RISC-V at the same time, right? Doesn't really work, but that's the demand. People would like to have all their things in there. And so one of the things we do at the foundation is manage how the ISA grows, the ISA roadmap. So this is actually happening. Some evidence for this. This is an independent analyst firm, Semico, went around and talked to folks who are planning RISC-V projects. And they were predicting over 60 billion RISC-V cores shipping in 25. There's well over 1 billion shipped in 21. And that's probably way under what actually shipped using RISC-V. And this is probably a very conservative estimate. So there's a lot of RISC-V on chips. Now these same chips may have other ISA cores on there, but RISC-V is commercial, it is shipping, it's out there in volume in lots of places, right? And the prediction is you're gonna see a lot more RISC-V in lots of commercial products. Remember, chip projects take a while. So as people adopted it, decided to use the IP, integrate it on the chip, qualify the chip, go through all those stages, it takes a few years to get a product to market to ship in volumes, but that's happening, and you see this ramp up happening now in silicon out there. Now, the other big thing that happened with RISC-V is education. We came from education. I have to say, initially, it was more industrial uptake than academic uptake, because the academics like, well, this is not real. I'm not going to change my slides. I'll stick to my old MIP slides for the next 20 years. But finally, the top schools changed their curricula, and that's the way the curricula spread. And there's tens of thousands of undergrads every year now who learn RISC-V in computer architecture classes, US and around the world. So it's really taken over in education. The advantage is all the labs, you can have real RTL in the lab and distribute it. You couldn't do that with the other ISAs, right? So that's why it's attractive, not just for teaching, but also for research, right? So why is this so popular? So I have to keep reminding people, because engineers, I'm sure a lot of you engineers, processor engineers fixate on, they don't really see the reason, because they're fixated on, is it happening because it's 10% faster or 30% lower power? Is that why people are excited about RISC-V? And no, it's because it's a completely new business model, and this changes everything, right? So the thing to understand is it's not about technical merit of the ISA. I wish to say, RISC-V is the best ISA ever. But when we started, we said we just want a boring RISC we can standardize. That was kind of the play. The important thing is the business model. This really changes everything. Because now as a customer, you first pick the ISA, then you pick the vendor. And that's really powerful, right? Previously, you picked a vendor for your core and you were stuck with their ISA. You built your software for their ISA. When you went to the next generation part, unless you wanted to rebuild your software for a different ISA, you kind of were stuck. You had to lock it. Right, so the real powerful thing is, everything's RISC-V. I can get everybody to compete for my business, the socket I want to put this thing in, right? Also, there's this flexibility. People can extend it and add stuff without getting permission. And we designed the ISA to allow extensibility without getting in the way of the standard software. So you can have standard software, but extensibility on the side. And we did that because we were building a research infrastructure, and we wanted to make sure we could do our experiments without messing up all the code porting we did. Right, and so that's another advantage. And because it's open, you get commercial, academic, open source communities. They can all coalesce around a single open standard, and that's very powerful. So everybody's working together on the same thing. There's no barriers to everybody cooperating around this single standard. So this is a slide I put together to clarify this. A lot of folks are not aware of some of these boxes and what they mean. Okay, let me go through this. So I just picked the 3 most popular ISAs, x86, ARM, and RISC-V. Let's talk about the business model. So let's start with x86. x86 is a microprocessor business model. Intel and AMD sell you chips, period. That's it. That's all you can do with x86. You can buy chips from a few vendors. You cannot get an architecture license to build your own x86. You cannot license a softcore x86. You cannot add your own instructions to x86. And you definitely cannot open source x86 IP. So all you can do with x86 is buy chips from AMD and Intel. And it used to be VIA as well, but now Intel's bought the design team. So it's basically 2 vendors left. That's all you can do with x86. And you may realize x86 is not being designed into any new applications. It has its place. It's being used very well in those places. But nobody, oh, I'm going to do this new application. Maybe I'll pick x86. That's not happening, right? Unless it's some app that runs on a server farm or something. That's all it's for. It has its place, a very limited business model. Now, ARM, of course, they came along and they developed this CPU IP licensing model. And so, yeah, there's many chips you can get from ARM. You can get an architecture license to design your own core, but it's very expensive. You can license commercial core IP, but only from one vendor. Sort of add your own instructions. A few of the cores, they added that in response to, I think, RISC-V pressure. But there's definitely no open source core IP. On contrast, RISC-V, yeah, there's many vendors who will sell you chips. The architecture license, everybody gets one for free. Just go read the spec. Commercial core IP, yeah, there's many vendors now. Over a dozen commercial core IP vendors. You can add your own instructions, and yeah, you can do open source core IP as well. So those of you who certain age grew up in the UK will recognize where I stole this tagline from an advertising campaign. RISC-V is the ISA that likes to say yes, right? So, you know, let's move on to what's happened with RISC-V. That's kind of the background. So we've been filling out the ISA, trying to manage this onslaught of feature requests. And you know, 2021 really was a big banner year for RISC-V in terms of completing and ratifying specs. Some have been in progress for a long time. So vectors, hypervisor, crypto, cache management, virtual memory enhancements, and a lot more extensions are in flight. So there's a lot of activity. RISC-V is really pushing along in terms of ISA extensions. Now people say, well, there's all these extensions. That's going to cause this fragmentation. It's horrible. How can you manage? You know, there's going to be dozens of incompatible RISC-V chips. That's really FUD. I mean, I don't see any evidence of this at all out there. And another thing is people confuse two things, fragmentation and diversity. So fragmentation is when you do the same thing 2 different ways for no good reason, right? And so, you know, left-hand drive, right-hand drive cars, right? Like, why does humanity need 2 different ways of driving a car? They don't. It's just a random choice that people pick differently in 2 different places. So now every car manufacturer has to support both options, right? If they want to be global, right? That's fragmentation, and that's bad. The good thing is diversity, right? If you're potting around Cambridge, a bike is a pretty useful thing to have, right? If you want to take 500 people across an ocean, you don't need a bike, you need a jumbo jet, right? So if you're solving a different problem, you have a different solution, and that's diversity, and that's fine. So RISC-V admits this kind of diversity, right? If you want to manage that fragmentation, that's what the standards body does, is say, this is the way you do X if you want to do X. But people confuse these 2 things and say diversity is bad. No, diversity is not bad. It's because you have such a wide range of solutions. Right. Now, how we avoid fragmentation. So one of the things people forget, they might think, oh, these vendors want to go off and get lock-in. You forget about 2 very powerful forces. One is users. Nobody wants to repeat a vendor lock-in. So I can tell you from SiFive sitting customer meetings, they'll say, is this standard, the thing you've added? If not, I'm less interested in it, right? I want to know that I can go have you compete with somebody else for the same design later, right? And software. So nobody can support their own software stack, right? And I think that's literally true. Everybody would like better software everywhere. And if you start fragmenting, having your own ISA features and widgets, you have to build and support that software stack for your customers. And it cannot be that good. And even nation states have realized this doesn't work, and so they don't do this anymore. So basically people worry about compatibility suites and RISC-V and everything, but basically if GCC doesn't work on your chip and Linux doesn't work on your chip, that's your problem. And you'll see that before your customers do. So fragmentation is actually much less of an issue than people make it out to be. It really isn't, because these big forces make sure it doesn't happen. So diversity, though, is another challenge. We have a lot of flexibility. There's a lot we can do with RISC-V. So how do we make it sane for the users? So the base RISC-V idea was you have a base instruction set, say a 64-bit ISA, and you can add lots of modules onto it. And this is great. You can highly tune a core for some market. But it ends up with a massive combinatorial explosion of options, which can overwhelm people. In some spaces, what you really want is what we call a profile, which lays down, you must have all these things in this form. And so the profiles are something we're pushing through this year. So basic profile, but then the key one most people will be looking at is the application processor profile, which has very few options and a lot of mandates. So there's a lot of things are fixed, and if you want to port a distro and have all the packages work, this is what you'll be targeting, is one of these profiles. So it basically makes the space much, much, much smaller. There's only a few actual options left once you've done this, and a lot of mandates. So that's how we're managing diversity there. And finally, the hardware side, we're also working on hardware platforms and standardizing those. Okay, so that was the RISC-V part of the talk. Let me just talk a little about what SiFive has been doing. So, we founded SiFive because we saw this big opportunity now that RISC-V was taking off back in 2015. So we just had our 7th birthday. So SiFive is now 7 years old. And we've done a lot in that time. And really view ourselves as the leaders. So we've grown a lot. So now the company is, I need to read the chart because I don't know these latest numbers. We have over 11 offices around the world, and especially, we're open this new one here in Cambridge. So very excited to be back here in Cambridge with a new office, and we're hiring. So please let us know if you're interested. And over 700 employees, and we view ourselves as leaders in RISC-V. So this is amazing to me, having remembered when there was just the 3 of us sitting in a room at the VC firm trying to figure out what we're going to do to this state. It's pretty amazing. So, at this point, we've over 300 design wins, over 100 different customers. And most of the big semiconductor companies work with us on RISC-V. So let's talk about some of the things we're doing that might stretch your concept of what is RISC-V. So the P650 is one we announced recently, and this is a high-end, out-of-order RISC-V application processor. So this is comparable to higher performance than, say, an A76, 12 plus spec int per gigahertz. A lot of facilities, trace debug, security features, a lot of stuff on there. Oh, the on-core cache coherence. So this is quite a sophisticated out-of-order core, quite a high performance level. We view it very competitive when we do PPA comparisons with our competitors. And we have more to come in this space. So this is just the most recent one we announced. You're going to see, onwards and upwards, faster, better, more efficient cores coming from us in this space. So this is a high-end applications core out of SiFive. But let's talk about diversity. So that's not the only dimension we look at. That's an interesting dimension. We're working on that. There's also all the other cores on an SoC, or when you're building a more specialized SoC. So we started this intelligence line to really take RISC-V vectors and sort of focus on that in the product. So the X280 has a very wide vector unit, 5 12-bit vector registers. It also has a bunch of extra custom extensions that SiFive's added to do AI kind of tasks. And this has been an incredibly popular product for us. It's something that's different from what's out there. It replaces different cores on the SoC, not the main core, but some other cores, or it's a specialized accelerator chip you're building. It has full Linux functionality. So unlike a classic DSP chip, this runs a regular RISC-V stack. It can run Linux. It has security features. It has a full RISC-V feature set plus the big wide vector unit on the side. And this is why we think it's been very successful. So just to give you some idea on the AI workloads, this is just one benchmark. You can see the benefit you get from adding the vectors, and on top of that, the extra benefit we get from adding our own custom instructions for those AI kernels. So, these AI kernels, they're a small amount of code compared to all the code you need to run inference on a Linux stack, but we can accelerate those a lot with our own special instructions we added in there, right? Now, the other thing, what we were a little bit surprised, we got a lot of design wins for X280, then we saw what people were doing with it. A bunch of our customers were using this as a companion core. So a lot of customers had built an AI accelerator, then they kind of realized they needed software. We need software to drive this accelerator. Where's that going to come from? So they started down the path of building their own widget to sit next to that big widget, and they realized there's no way they can support the software. So what they realized with the X280, it provides the full software stack, plus it has vectors. So it can do all the around the edge work that their big engine cannot do well or is not capable of doing. And so it acts as a companion. It sits alongside the big accelerator and does all the cleanup work and integrates it with a full software stack. So this companion core model we saw being very popular, and so we then doubled down on that and added a new vector coprocessor interface that allows the accelerator to talk directly to the vector registers inside the X280. So there's a very high bandwidth path in and out of the vector registers to the accelerator, And you can either use this to connect to a big accelerator of your own, or you can use it to add new custom instructions of your own as well. But those custom instructions are tied directly into that big vector unit, can be driven at speed. So this has been a very popular thing. This has been driven by this customer use case we saw, a companion core. So this is an example of customers looking at not the application core, but these other cores that are also important, and moving to RISC-V there. And a lot of people like the idea that eventually everything will be RISC-V on the chip, not just the main core. So just give you some idea where SiFive is going. So we divided our product line into these three categories: performance, intelligence, essential. Essential, the microcontroller class products, up to very small apps processors. Intelligence is this new line of vector enhanced cores with extra extensions, and we're going even further on vectors, so even more numeric performance on those in the future. The out-of-order cores are classic application processors, adding more features and increasing the performance, adding vectors to those as well. And we expect to be, on parity with our competitors pretty soon, and past them pretty soon as well. So you're going to see up and to the right this development. Now, one reason we can move very quickly is the way we develop the cores internally. It's a methodology originally developed out of Berkeley, based on Chisel and a lot of generators. And this allows us to more rapidly develop IP. And one thing we're using is not just the way we write the cores, but all the transforms we do on the cores, moving to support automotive as a feature in the core family. So we're basically going through and adding automotive capabilities to most of the cores in the line over time, both ASIL Bravo, ASIL Delta, including versions of split lock as well as just dual core lockstep. So all these features we're adding in a more intelligent way. You may ask, how can we move this fast with this few people? Part of it is we have great people, and we like to hire more great people. And part of it is the technology we have at the company to develop these cores. Okay, so that's where we're going, just better and better over time. And the other part about the story, software, like I keep saying, software is king. So we have a big investment in developing software to help support our customers use the products. So don't want to go through this in detail, but we're also, developing a lot of software and want to recruit a lot more folks to work on software with us, because we see that as essential to get these products out there. Okay, so the message I want to leave is RISC-V has no limits. Whatever preconceptions you have that RISC-V can only do this, only do that, that's wrong. It's going to be everywhere doing everything over time. And we hope SiFive is the one that's selling you those cores that do everything over time. So happy to take questions now. So that's it.
Hi.